A ball is thrown straight up. At the top of its path, the acceleration is. So if I throw a ball up and it comes back down, if it leaves my hand with a magnitude of 20 meters per second, we know it's going to return at 20 meters per second. The velocity will, at least looking at magnitudes, not indicating directions. So we know the magnitudes are going to be the same because as this ball goes up, it's going to slow down. As it reaches the vertex, we know the velocity at the vertex is 0 meters per second because it's changing direction. So at some point, at its highest point, it stops just for a split hair of a second. You can't even tell, but it changes directions. So it goes up, slows down, gets to its vertex, it stops, it changes directions, and then it starts to speed up as it comes down. It's going to accelerate because of acceleration due to gravity. But acceleration due to gravity, if I'm looking at the magnitude, it's going to be 9.8 meters per second squared here. It's going to be 9.8 meters per second squared here. If I want to include direction, it's going to point down over here. Acceleration is also going to point down over here. So acceleration is constant, okay, for at least for our calculations. They're 9.8 everywhere. At least that's how we're going to calculate it. In real life, it's not the case, but for our classroom, that's what we're going to say. So if I pick any point, my acceleration is going to be 9.8 meters per second squared here. It's going to be 9.8 meters per second squared here. It's going to be 9.8 meters per second squared here. Now, velocity is going to change, but our acceleration isn't. So at the top of its path, acceleration is going to equal 9.8 meters per second squared because it is a constant.